everyone, welcome back to Math 3322, Math Concepts 2. Today we're going to look at Chapter 7, Section 5. So Section 7.5 is all about real numbers. So you should be able to understand and explain real numbers, operations on real numbers, nth roots on and square roots, how a to the power 1 over n and a to the power n over m are defined and why, and expressions involving radicals and radical exponents, especially solving equations or simplifying expressions involving those. So real numbers are numbers that can be expressed as a decimal. So they can either be a terminating decimal or a repeating decimal if they're rational, but if they are irrational, then they have a non-terminating, non-repeating decimal, and those are called irrational numbers. So irrational numbers have to be have an infinite number of non-zero digits to the right of a decimal point, and there can't be a repeating block of digits. Square roots are one example of where we see irrational numbers show up a lot, but a square root is derived from the area of a square. So the area of a square is calculated by taking s, the side length of a square, and multiplying it by itself. So s times s is s squared. So the area of a square is, with a side of 11, would have area 121. If we know the area, then we can calculate the length of the side by taking the square root. So if we know the area of a square is 49, then the length of a side would be the square root of 49, which would be 7, or -7, because -7 times -7 is still 49. However, if we're talking about area and length, -7 doesn't make sense in that context because we can't have a side length that's a negative value. All right, so square roots are a number a of a number a is a number x such that x squared equals a. And we call the principal square root of a, which is just denoted with the square root symbol, it's the non-negative number x such that x squared equals a. So in that last example, 49, the square root of 49 could be 7 or -7, but the principal square root is just 7, the positive version. So the square roots of 144 are 12 and -12, because we need to think about both of those, negative and positive. The principal square root of 144, though, is just the positive version. So we're going to have just positive 12. Now, when we want to simplify the square root of 4 over 9, we are again talking about the principal square root because we're using that radical symbol. But we can simplify this to be the square root of 4 over the square root of 9, because square root is multiplicative, meaning it applies to things being multiplied. So if we think about this as like 4 times 1 over 9 to get our 4 over 9, then we can apply the square root to both of those. The square root of 4 is 2, and the square root of 9 is 3, because we're talking about the principal square root in both of those. So the square root of 4 over 9, principal square root, is just 2 over 3, or 2/3. So other roots, we can take roots that are not just the square root. So we denote that as the square root symbol with an n now in the corner. So the square root of x, we would call this the nth root of x. So if x is even and positive, then the principal nth root of x is positive, just like we had with square roots. Now, if n is even and we have a negative value under that radical symbol, then the nth root of x is not a real number, because we can never have a thing multiplied, a negative number or any number multiplied by itself an even number of times and get a negative number, because negative times negative is positive, and positive times positive is positive. So we can't ever get the nth root of a negative number if that number is negative. But, or sorry, if n is even. If n is odd, however, we can have the nth root if the number under the radical is negative. So for example, this cubed root of -8. -8 we can get by saying -2 times -2 times -2, or -2 cubed. So the cubed root of -8 is -2, because if we multiply it to itself 3 times, we do indeed get the number we were looking for. And if we ever have the square root of a number squared, then we get the absolute value of that number. So the square root of 4 squared is just the absolute value of 4, or 4 itself. So we can typically tell that a number is going to be irrational if it contains a root or radical in its simplest form. So for example, if we want to tell if the cubed root of -250 is rational or irrational, we can simplify that number. So -250, or just 250, we can factor into 25 and 10. And then 25 is 5 times 5, 10 is 5 times 2. So 250 is equal to 5 cubed times 2, because I have 3 5s and 1 2. So when I go to take the cubed root of -250, that's going to be equal to negative cubed root of 250, because of that rule I just mentioned to you. And so this is negative cubed root of 5 cubed times 2, because 250 is 5 cubed times 2. Now, again, because the radical symbol is multiplicative, I will have negative cubed root of 5 cubed times cubed root of 2. So that's -5, because cubed root of 5 cubed is 5 itself, and times the cubed root of 2. So this is going to be an irrational number because we have our root symbol in the simplest form. Okay, so when we think about the system of real numbers, it's all of the rational numbers and irrational numbers, both of those sets unioned together. So all rational numbers and real and irrational numbers put together give us all of the real numbers. The decimal form of any real number is either terminating, repeating, or non-repeating. And every integer is a rational number, and every rational number is a real number. So we have every integer is a real number. Every rational number is a real number, but not every real number is rational. For example, the cubed root of 2 is a real number, but it is not rational. Here's a nice chart, I think, that can help you visualize what's happening here. So this square represents all of the real numbers. And then inside, if we start with the natural numbers, which are our counting numbers, starting at 1, and then the whole numbers are those same counting numbers, including 0. Then integers are the negative and positive counting numbers. Rational numbers are any numbers that we can put into a fraction of integer values. And irrational numbers are those numbers that cannot be put into a fraction of integers, and we'll have that non-terminating, non-repeating decimal. And there's some examples here. And so again, these are the definitions, and showing you that they are nested within one another. So the real numbers have several properties that are really useful for us in mathematics. So the closure properties tell us that if we have any A and B in the set in the real numbers, then their sum and their product are going to be real numbers. So we can't get anything outside of the real numbers when we add or multiply any two real numbers together. We also have commutativity, or commutative property, for multiplication and addition. So if we have real numbers A and B, A plus B is equal to B plus A, and A times B is equal to B times A. Then our associative properties tell us that grouping in our operations with 3 elements doesn't matter. So if we have real numbers A, B, and C, then we can add together B and C and then add A to it, or we could add A and B together and then add C together with it, and we'll get the same result. And the same is true of multiplication. We can group numbers together in any order we like, as long as we're doing all addition or all multiplication. The real numbers have a couple of identities, so special numbers that don't change what happens when we add or multiply them. So the number 0 is our additive identity because anything plus 0 is itself, and 1 is the multiplicative identity because anything times 1 is equal to itself. And something interesting about the real numbers is that they all also have inverses for addition and multiplication. So for every real number A, negative A is its additive inverse, because if we take A plus negative A, we get 0. And if we have that same number and we want its multiplicative inverse, 1 over A is the multiplicative inverse because A times 1 over A is equal to 1. And then finally, we have one property that combines addition and multiplication for us, and that's the distributive property, and it works over addition and subtraction. So what it tells us is if I have some element A times the sum of B and C together, then that's going to be equivalent to if I do A times B and then add A times C. So I distribute A over the sum of B and C, and similar for the subtraction. And then for all real numbers, if we multiply it by 0, we get 0. And then finally, for real numbers A and B, there's always a number C in between them. So this is something that we don't get like in the integers, for example. So if we take 1 and 2 in the integers, there's no number between 1 and 2 that's also an integer. But in the real numbers, we can take any 2 real numbers and we can always find a number between them. So for example, 1 and 2, 1.5 is between 1 and 2. Between 1.5 and 2, 1 and 3/4, and etc. You can keep finding numbers in that way. And we call that the denseness property, or that the real numbers are dense. So if we have a fractional exponent or rational exponent, and x is a real number, and n and m are both integers, then we can, the way we define x to the 1 over n power is that's just the nth root. So for example, a to the 1/2 power would just be the square root of a. X to the m over n power, this is the same thing as if we had x to the 1 over n to the mth power, and that's the nth root of x to the m, or the nth root of x to the m inside. Those two things are equal. All right, so we have properties of integer exponents. Those also hold for rational exponents. So multiplying exponents together, adding them. So if we have a to the n times a to the m, that's equal to a to the n plus m. And if we have a to the n to the m power, that's a to the n times m. And the same thing is true whether n and m are integers or if they are rational numbers. Okay, so we're going to spend quite a bit of time going through some of these examples. We already talked about a on a previous slide, but the goal of this is to simplify these radical expressions. So if I want to simplify the 5th root of 96, what I want to do is I want to factor 96 as much as I can down to its prime factorization. So 96, I first see that this number is going to be divisible by 3, and that's because both of the digits are divisible by 3. So 96 divided by 3 should give me 32. And 32 is 4 times 8. 4 is 2 times 2. 8 is 2 times 4, and 4 is 2 times 2. So I have 1, 2, 3, 4, 5 2's. 2 to the 5th times 3 is the prime factorization of 96. So if I want to take the 5th root of 96, that's going to be the same thing as the 5th root of 2 to the 5th times 3, which by that multiplicative property, I have the 5th root of 2 to the 5th times the 5th root of 3. The 5th root of 2 to the 5th is just 2. And there is no 5th root of 3, so this is as simple as we can get it. 2 times the 5th root of 3 for 96. Now, for the cubed root of 16, again, I'm going to take 16 and I'm going to factor it as much as I can. So 16 is 4 times 4. 4 is 2 times 2. So 16 is equal to 2 to the 4th power. Now, something I want you to observe here is that 2 to the 4th power is the same thing as 2 times 2 times 2 times 2. And we can group those together by the associative property that we can have 2 cubed times 2. That's the same thing. So the cubed root of 16 is the same as the cubed root of 2 cubed times 2, which is the same as the cubed root of 2 cubed times the cubed root of 2. The cubed root of 2 cubed is 2 times the cubed root of 2. So this is our simplest version for part C. All right, lastly, we have negative 32, the 5th root of negative 32. And since this is an odd value, this is going to exist and it will be equal to negative the 5th root of 32. 32 is 4 times 8. We just did this a moment ago. 8 is 4 times 4. No, it's not 4 times 4, it's 4 times 2. And then 4 times is 2 times 2 on both of these. So 32 is 2 to the 5th power. So negative 5th root of 32 is negative 5th root of 2 to the 5th, or just negative 2. Okay, so that's one of the things that you need to be able to do from this lesson. All right, so if we start working with simplifying expressions with these radical exponents, or excuse me, rational exponents, we need to think about what these roots, what these exponents mean in terms of roots. So 16 to the 1/4 power means the 4th root of 16. 16 is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. 16 is 2 to the 4th power. So it's the 4th root of 2 to the 4, which is 2. What we could also do is replace 16 with 2 to the 4th and then use that multiplicative property of exponents and multiply 4 and 1/4 together. And that's why the 4th root of 2 to the 4th cancel out each other. All right, so if we do 16 to the 5/4 power, again, I know that the 4th root, this is the 4th root of 16 to the 5th power. I just did the 4th root of 16 and it's 2, so it's 2 to the 5th power, or 32. All right. Then if we look at negative 8 to 1/3, so this is the cubed root of negative 8. That is going to exist because we're taking an odd root of a negative number. So that's the same thing as negative cubed root of 8. 8 is equal to 2 times 4, which is 2 times 2, which is 2 cubed. So this is negative 2. Because we're taking the cubed root of 2 cubed, and we have the negative because of that original negative. And then 125 to the negative 4/3 power. This is going to be the cubed root of 125 to the negative 4th power. 125 is 5 times 25, which is 5 times 5. So it's 5 cubed. So the cubed root of 125 is 5. But then I have to the negative 4th power. So this should be what a negative power does to a number is it makes it in a denominator of a fraction. So this is the same thing as 5 to the 4th under 1. And that should be 100 or 625. So just to remind you, a to the negative 1 power is equal to 1 over a. That's how we got from this step to this step. All right, and then last but not least, we have negative 16 to the 1/4 power. So this is the 4th root of negative 16. And what you should see from this one is that we have no solution. It's not a real number because we have an even root of a negative number, and that's impossible to get in the real numbers. All right, and then lastly, these are pretty challenging examples for a lot of students, so I wanted to walk through an example. So what the goal of these questions is to solve for x, to find what numbers for x could satisfy the equation. So if we look at this first example, 3 to the x equals 81, then my goal is to write 81 as 3 to some power and then compare x with that power. So 81 is 9 times 9, and 9 is 3 times 3. So 81 is 3 to the 4th power. So I can write 81 as 3 to the 4th power. And since 3 to the x equals 81, or 3 to the 4th, I know that x has to equal 4 in this example. All right, so if we look at the next one, 9 to the negative x equals 243. Again, I want to write 243 as some power of, with 9 as the base, 9 to some power. So what I would do here is I'm going to just divide 243 by 9. And you can do this by hand. You can use a calculator. I'm going to use a calculator right now for brevity. But if I take 243 and divide by 9, I get 27. And then if I divide by 9 again, I'm left with 3. So this is 9 times 9 times 3. So it's 9 squared times 3. So the easiest way for me to see this number is to remember that 3 is actually the square root of 9. So I can rewrite 3. So I have 9 squared. 3 is the same thing as the square root of 9, which is 9 to the 1/2. And so when I'm multiplying values with the same base and different exponents, what I need to do is add those exponents together. So I get 9 times, or to the 2 plus 1/2, 2.5, which is the same as 5/2 power. So 9 to the negative x is 9 to the 5/2, which means that x is equal to negative 5/2. And then you can always check your answer by putting into a calculator 9 to the 5/2 power and seeing that it should equal 243. Okay, if we look at example C, so we have 9 over 25 to the 3x equals 3,125 over 243. Now, in the previous example, I just figured out that 9 to the 5/2 power is 243. So I'm going to go ahead and replace that because I know it's going to be relevant to my problem because my goal is to get this number into some form with 9 over 25. So if I say 3,125 over 9 to the 5/2, because 9 to the 5/2 is 243. Now, I want my number to be 9 over 25, not 25 over 9 or something over 9. So the next thing I'm going to do is I'm going to multiply both of these sides of the equation by, or I'm going to take the negative root. So I am going to say 9 over 25 to the negative 3x. That will be equal to 3125 over 9 to the 5/2 to the negative 1, which is the same as 9 to the 5/2. Let me write that a little clearer. 9 to the 5/2 power over 3,125. Now I need to write 3,125 as some power of 25. So if I, again, take 3,125 and divide it by 25, I get 125. And 125 is 25 times 5. And again, this just like the 9 and 243 situation, I have 25 squared times the square root of 25, because 5 is the square root of 25. So that is, again, 25 to the 5/2 power, which works out really nicely for us because now I have 9 to the 5/2 over 25 to the 5/2. And, oh, let me make some room here. Which is the same. I can take that exponent out because of the multiplicative property, 9 over 25 to the 5/2 power. So I know now negative 3x equals 5/2. So if I divide both sides by negative 3, I will get negative 5 over 6. And again, you can check your answer here by plugging in negative 5, 6 into our original equation. It's not letting me erase this. Well, let me stop sharing and reshare. Okay, so we're moving on to the next example, which is here part D. The square root of negative x equals 3 times the square root of 5. So this one's a little bit simpler because what we need to do is we remember that square root means a power of 1 over 2. And if we want to get rid of that, we can square the value. So if I take the square of both sides, then I'm going to get the square root of negative x squared equals the square root, or 3 times the square root of 5 squared. So this gives me negative x equals 3 squared times square root of 5 squared, which is 9. Square root of 5 squared is just 5. Nine times 5 is 45. Negative x is 45. So x equals negative 45. So when I go back and I think about my final solution to this question, I know that I'm going to have the square root of a negative, but the thing that I'm putting in there is a negative. So the negative 45 is just 45. And we can't have a positive value in that, or else we'll be taking the square root of a negative, which is not a real number. Okay, then x to the negative 3 over 25. So here, if you've taken any college algebra or you remember from high school algebra, one way to do problems like this is to take logarithms. But I mean, for A, B, and C. But I think here we can just think, okay, what do I need to raise this power to have no power here? So if I take x to the negative 3 over 25, and I raise it to the negative 25 over 3, I also have to do that to 5. Then I'll get x equals 5 to the 25, negative 25 over 3 power. So 5 to the negative 25 over 3 power is 3, the cubed root of 5 to the 25th power. And that's actually, excuse me, negative 25. So that's 1 over the cubed root of 5 to the 25th power. So that is what our x needs to be. Oh, sorry. And then last example, I have x minus 1 squared equals 5. So if I take x minus 1 squared and I take the square root of both sides, I'll have x minus 1 equals the square root of 5. And then, but the problem I need to watch out for here, because I've taken the square root, is this can be either positive or negative. So x equals 1, if I add 1 to both sides, plus or minus the square root of 5. So 1 plus the square root of 5, or 1 minus the square root of 5. And that's because I imposed the square root myself. And we weren't asked for the principal square root. All right, so I know this was a bit long, but I hope you found this helpful. Let me know if you have any questions, as always.